Hello everyone, and today we will be talking about internal energy. And you'll recall that internal energy is given the symbol U, and that we can describe total internal energy as the heat plus work. But if we take a step back, we can also summarize the total energy of a system as the energy of translation and the way that that applied using kinetic molecular theory, the energy of rotation plus the energy of vibration and the energy of electronic transitions. And I'm forgetting the plus right there. And for translational energy, we found that the kinetic energy of a particle is the integral of the work from a starting velocity equal to 0 to a final velocity Vx. And we summarize that as delta K equals W equals the force times that displacement. And if we went ahead and integrated with respect to velocity from 0 to some final velocity, we found that we saw the relationship as being equal to 1/2 mv squared, or the kinetic energy. As we continued that conversation about translational energy, we found that each translational degree of freedom was equal to 1/2 kT for an individual atom, or was equal to 1/2 RT for a mole of a particular gas. And so if we wanted to consider all translational degrees of freedom, we would find that we have 3/2 kT for X, Y, and Z, or 3/2 RT for X, Y, and Z. Of course, that being for a mole of our gas. And if we need to, just to recall, we'll go ahead and draw our Cartesian coordinates and show that we can in fact move in X, Y, and Z, and this ability to move is again a way to store energy. And then we can begin to have a conversation about rotational energy as well. But let's at least summarize that U, or this internal energy, if dealing with translation, would be equal to 3/2 RT. And so let's keep that in the back of our head. The storage of energy in the degrees of freedom of a molecule is summarized with the equipartition function. Or excuse me, the equipartition theorem. I apologize. And basically it states that each degree of freedom, which we'll summarize as DOF, can store 1/2 kT of energy. And so, as our example, which we commonly use here in Chem, is for N2. And we would show that for translation, we've got 3 degrees of freedom. For rotation, we've got 2 degrees of freedom. The rest of that F needs to go in there. And for our vibrational degree of freedom, we would have 1 DOF. And if we wanted to look at the degrees of freedom for N2, what we would end up using, again, if we want to draw a picture over here in the corner, in our Cartesian coordinates, and we've got our N2 molecule, the only way that it's going to vibrate is by stretching along the internuclear axis in such a fashion. And when we want to calculate this, we can say that the degree of freedom will be equal to 3n minus 5 for a linear molecule, and would be 3n minus 6 for a nonlinear molecule. And as you can imagine, with n equaling 2, 3 times 2 minus 5 equals 1, which is consistent with a linear stretch of n2.